Hello, ladies and gentlemen. My name is Nababan. I'm from School Member Institute of Technology, and currently I'm majoring in physics. So, in this occasion, I'm going to show you my physics project. So, without further ado, let's get started. Okay, so these are the materials I'm using on this physics project. So we get some ropes, a straight metal rod, 3 spar springs integrated with hooks, and 1 load. The spar springs I'm using here are approximately same in mass and spring constant. This is also a rough sketch of the system I'm going to use. And now, let's set the system. Okay, so this is the overall system I'm using on this project. First of all, I'm using both the mirror rod and the springs. It is because to prevent the spare springs to move around the mirror rod. The mass of the spare springs and the ropes are much smaller than the mass of the load. So it is safe to assume that the mass of the spar springs and the ropes are negligible. So their mass effect on the motion of the system is negligible too. The system moves when you put a force on the load like this, and the system will oscillate up and down like this. The concern for this system is that the load only can move on y direction, on y axis. Direction is when the load moves, let's say x-axis or z-axis, it will oscillate, but also it will move on a circular path. So when it moves on a circular path, we can consider the load as a point object, because a circular path requires the moment of inertia of the load. And if we want to calculate the moment of inertia, we will consider its dimension. But earlier we assumed that the load as a point object, so it contradicts. So the load cannot be moved on x-axis or x-axis and z-axis. It only moves on y-axis. Also, here the metal rod, it has to be stationary. Actually, the mirror can move like this, so it rotates on y-axis, and it can rotate on like this, like on z-axis. Yeah, so the metal rod can move on y-axis, like this, and z-axis like this. But again, if the mirror rod is rotating on whatever it can rotate, the load will move in a circular path, and again require the moment of inertia of the load. And again, if moment of inertia of the load is required, we can consider the load as a point object. So the total constraint for this system is 4, and the degree of freedom of this system is 1 because it only moves on one direction.
As I said before, all of the spiral springs have approximately the same spring constants. The system I'm using is equivalent to the diagram you see on the screen. If each of the spiral spring has a spring constant K, then the system is equivalent to one system spiral spring with the spring constant is equal to 2/3 of K. If we consider the system has no damping force, then the equation of motion of the system is my double dot plus ky is equal to 0. And the solution of this equation is y is equal to a sine omega t plus phi. But if we consider the system has damping force and the air friction force is proportional to the velocity of the system, then the equation of motion of the system is my double dot plus by dot plus ky is equal to 0. And the solution is y is equal to a, or amplitude, times e to the minus b times t over 2m times sine of omega xn times t plus phi, where omega xn is equal to square root of k over m minus b squared over 4m squared.
Okay, that's all from me. Thank you for watching. I'll see you on the final round. Bye!